I'm really glad to be here. I'm glad you're here, because that would be a little weird. I'm glad we're all here. And by here, I don't mean here. Or here. But here. I mean Earth. And by we, I don't mean those of us in this auditorium, but life. All life on Earth. From complex to single-celled, from mold to mushrooms to flying bears. And the interesting thing is that Earth is the only place we know of that has life. 8.7 million species. We've looked other places, maybe not as hard as we should or we could, but we've looked and we haven't found any. Earth is the only place we know of with life. Is Earth special? This is a question that I've wanted to know the answer to since I was a small child, and I suspect 80% of this auditorium has thought the same thing and also wanted to know the answer. And to understand whether there are any planets out there in our solar system or beyond that can support life, the first step is to understand what life here requires. And it turns out, of all of those 8.7 million species, life only needs three things. On one side, all life on Earth needs energy. Complex life, like us, derives our energy from the sun. But life deep underground can get its energy from things like chemical reactions. There are a number of different energy sources available on all planets. On the other side, all life needs food or nourishment. And this seems like a tall order, especially if you want a succulent tomato. However, all life on Earth derives its nourishment from only 6 chemical elements, and these elements can be found on any planetary body in our solar system. So that leaves the thing in the middle as the tall pole, the thing that's hardest to achieve. Not moose, but water. Although moose would be pretty cool. And not frozen water, but water, and not water in a gaseous state, but liquid water. This is what life needs to survive, all life. And many solar system bodies don't have liquid water, and so we don't look there. And other solar system bodies might have abundant liquid water, even more than Earth, but it's trapped beneath an icy shell. And so it's hard to access, it's hard to get to, it's hard to even find out if there's any life there. So that leaves a few bodies that we should think about. And so let's make the problem simpler for ourselves. Let's think only about liquid water on the surface of a planet. There are only 3 bodies to think about in our solar system with regard to liquid water on the surface of a planet, and in order of distance from the sun, it's Venus, Earth, and Mars. And you want to have an atmosphere for water to be liquid. And you have to be very careful with that atmosphere. You can't have too much atmosphere, too thick or too warm an atmosphere, because then you end up too hot, like Venus, and you can't have liquid water. And if you have too little atmosphere and it's too thin and too cold, you end up like Mars, too cold. So Venus is too hot, Mars is too cold, and Earth is just right. You can look at these images behind me and you can see automatically where life can survive in our solar system. It's a Goldilocks type problem, and it's so simple that a child could understand it. However, I'd like to remind you of 2 things from the Goldilocks story that we may not think about so often, but that I think are really relevant here. Number 1, if Mama Bear's bowl is too cold when Goldilocks walks into the room, does that mean it's always been too cold? Or could it have been just right at some other time? When Goldilocks walks into the room, determines the answer that we get in the story. And the same is true with planets. They're not static things. They change, they vary, they evolve. And atmospheres do the same. So let me give you an example. Here's one of my favorite pictures of Mars. It's not the highest resolution image, it's not the sexiest image, it's not the most recent image, but it's an image that shows riverbeds cut into the surface of the planet. Riverbeds carved by flowing liquid water. Riverbeds that take hundreds or thousands or tens of thousands of years to form. And this can't happen on Mars today. The atmosphere of Mars today is too thin and too cold for water to be stable as a liquid. This one image tells you that the atmosphere of Mars changed, and it changed in big ways. And it changed from a state that we would define as habitable, because the 3 requirements for life were present long ago. Where did that atmosphere go that allowed water to be liquid at the surface? Well, one idea is that it escaped away to space. Atmospheric particles got enough energy to break free from the gravity of the planet, escaping away to space, never to return. And this happens with all bodies with atmospheres. Comets have tails that are incredibly visible reminders of atmospheric escape. But Venus also has an atmosphere that escapes with time, and Mars and Earth as well. It's just a matter of degree and a matter of scale. So we'd like to figure out how much escaped over time, if we can explain this transition. How do atmospheres get their energy for escape? How do particles get enough energy to escape? There are two ways, if we're going to reduce things a little bit. Number one, sunlight. Light emitted from the sun can be absorbed by atmospheric particles and warm the particles. And yes, I'm dancing, but they... oh my God, not even at my wedding. Okay. And they get enough energy to escape and break free from the gravity of the planet just by warming. A second way that can get energy is from the solar wind. These are particles, mass, material that are spit out from the surface of the sun, and they go screaming through the solar system at 400 kilometers per second, sometimes faster during solar storms, and they go hurtling through interplanetary space towards planets and their atmospheres. And they may provide energy for atmospheric particles to escape as well. And so this is something that I'm interested in because it relates to habitability. So I mentioned that there were two things about the Goldilocks story that I wanted to bring to your attention and remind you about. And this second one is a little bit more subtle. If Papa Bear's bowl is too hot and Mama Bear's bowl is too cold, shouldn't Baby Bear's bowl be even colder for following the trend? This thing that you've accepted your entire life, when you think about it a little bit more, may not be so simple. And of course, distance of a planet from the sun determines its temperature. This has to play into habitability, but maybe there's some other things we should be thinking about. Maybe it's the bowls themselves that are also helping to determine the outcome in the story. What is just right? So I could talk to you about a lot of different characteristics of these three planets that may influence habitability, but for selfish reasons related to my own research and the fact that I'm standing up here holding the clicker and you are not, I would like to talk for just a minute or two about magnetic fields. Earth has one, and Venus and Mars do not. Magnetic fields are generated in the deep interior of a planet by electrically conducting, churning fluid material that creates this big old magnetic field that surrounds Earth, and if you have a compass, you know which way north is. Venus and Mars don't have that. If you have a compass on Venus and Mars, congratulations, you're lost. Does this influence habitability? Well, how might it? Many scientists think that a magnetic field of a planet serves as a shield for the atmosphere, deflecting solar wind particles around the planet in a bit of a force field type effect having to do with electric charge of those particles. I like to think of it instead as a salad bar sneeze guard for planets. Okay? And yes, my colleagues who watch this later will realize this is the first time in the history of our community that the solar wind has been equated with mucus. Okay, so the effect, then, is that Earth may have been protected for billions of years because we've had a magnetic field. Atmosphere hasn't been able to escape. Mars, on the other hand, has been unprotected because of its lack of magnetic field. And over billions of years, maybe enough atmosphere has been stripped away to account for a transition from a habitable planet to the planet that we see today. Other scientists think that magnetic fields may act more like the sails on a ship, enabling the planet to interact with more energy from the solar wind than the planet would have been able to interact with by itself. The sails may gather energy from the solar wind. The magnetic field may gather energy from the solar wind that allows even more atmospheric escape to happen. It's an idea that has to be tested, but the effect and how it works seems apparent. And that's because we know energy from the solar wind is being deposited into our atmosphere here on Earth. That energy is conducted along magnetic field lines down into the polar regions, resulting in incredibly beautiful aurora, if you've ever experienced them. It's magnificent. We know the energy is getting in, and we're trying to measure how many particles are getting out, and if the magnetic field is influencing this in any way. So I've sort of posed a problem for you here, but I don't have a solution yet. We don't have a solution. But we're working on it. And how are we working on it? Well, we've sent spacecraft to all 3 planets. Some of them are orbiting now, including the MAVEN spacecraft, which is currently orbiting Mars, which I'm involved with, and which is led here out of the University of Colorado. It's designed to measure atmospheric escape, and we have similar measurements from Venus and Earth. And so once we have all our measurements, we can combine all these together, and we can understand how all 3 planets interact with their space environment, with the surroundings, and we can decide whether magnetic fields are important for habitability or not. Once we have that answer, why should you care? I mean, I care deeply. And financially as well, but deeply. First of all, an answer to this question will teach us more about these 3 planets, Venus, Earth, and Mars. Not only about how they interact with their environment today, but how they were billions of years ago, whether they were habitable long ago or not. It'll teach us about atmospheres that surround us and that are close. But moreover, what we learn from these planets can be applied to atmospheres everywhere, including planets that we're now observing around other stars. For example, the Kepler spacecraft, which is built and controlled here in Boulder, has been observing a postage stamp-sized region of the sky for a couple of years now, and it's found thousands of planets in one postage stamp-sized region of the sky that we don't think is any different from any other part of the sky. We've gone in 20 years from knowing of 0 planets outside of our solar system to now having so many that we don't know which ones to investigate first. Any lever will help. In fact, based on observations that Kepler's taken and other similar observations, we now believe that of the 200 billion stars in the Milky Way galaxy alone, on average, every star has at least 1 planet. In addition to that, estimates suggest that there are somewhere between 40 billion and 100 billion of those planets that we would define as habitable in just our galaxy. We have observations of those planets, but we just don't know which ones are habitable yet. It's a little bit like being trapped on a red spot on a stage and knowing that there are other worlds out there and desperately wanting to know more about them. Wanting to interrogate them and find out if maybe just 1 or 2 of them are a little bit like you. You can't do that. You can't go there. Not yet. And so you have to use the tools that you've developed around you for Venus, Earth, and Mars, and you have to apply them to these other situations and hope that you're making reasonable inferences from the data and that you're going to be able to determine the best candidates for habitable planets and those that are not. In the end, and for now, at least, this is our red spot right here. This is the only planet that we know of that's habitable, although very soon we may come to know of more. But for now, this is the only habitable planet, and this is our red spot. I'm really glad we're here. Thanks.